that exists. Normally what's used at a constant controlled current, constant current, because then the integral of I dt is the integral of a constant. Integral of a constant, you bring it out of the integral, it's I times t. So that's essentially an absolute. If it doesn't change, you know what that integral is. If it changes with time, then you know have to model what the decay is of the integral. It's not, maybe there's going to be some noise on it, maybe it'll be an exponential decay, whatever. The traceability of the amount of substance content, that's the number of moles per kilogram of sample, is to Faraday's law and the measurements of the current, the temperature, the current, the time, not the temperature, the current, the time, and the mass. Traceability of the mass fraction, which you might think of like for a high purity compound, it might be 99.99% KCl. You have also to include the uncertainty of the molar masses, what you may think of as atomic weights, potassium and chloride. Potassium and chloride, they're both mixtures of two or more isotopes. And those change with different samples. So you have to know what the uncertainty of the molar mass, and if you don't use the IUPAC tabulated values, which are an average of everything that's out there, what IUPAC estimates for nature, then you have to go and do mass spectrometry and get the relevant isotopic ratios for that sample. For benzoic acid that Jason just did, that he got something like 0.0051% uncertainty. And the uncertainty of the carbon, hydrogen, and oxygen that make up benzoic acid, those change enough that the uncertainty of the mass fraction of benzoic acid, the relative uncertainty in a percentage, if you will, would be significantly higher than it would be for amount of substance content, because the amount of substance content times the molar mass gives you the mass fraction. Each one of those has an uncertainty. So it's better to do this, but people are not used to thinking in terms of this. People are used to thinking, oh, it's 99.92%, whatever the chemical is you bought. For titrometric SRMs, you're using this primary ratio method, gravimetric titrometry. Traceability is to the titrant, which itself was standardized using the coulometric method. Conductometric SRMs, what is used for the SRMs is a secondary method. We prepare gravimetrically, very accurately, a potassium chloride solution from SRM potassium chloride. That goes back to a coulometric analysis of exactly known molality, the same molality which was used for the primary measurement in the past. The traceability is back to the primary measurement. What's the traceability of the primary measurement? Back to physical measurements, electrical resistance, and the diameter and length of this center tube if you're using that primary measurement technique. Spectrometric standard solutions. Now we're away from electrochemistry, but there may be some interest in this. NIST has a large program issuing, this is the periodic table, standard solutions, single element standard solutions for all the elements you see there. Those are used as then calibrants for spectrometric analysis techniques. They can be used for anytime you need a solution of element X with a standard, with a known value and known uncertainty, generally for trace analytical technique. So their mass fraction is 1,000 milligrams per kilogram, 0.1%, 1 part per thousand of each of the elements. A couple of them are different. Most of them are 1,000 milligrams per kilogram. ppm, not 1,000 milligrams per liter. People call that ppm. No, it's 1,000 milligrams per kilogram. It's dimensionless. And how do you make them? Well, first, how are they packaged? If you put it in a bottle, the bottle is porous. If you leave it around for a few years, some of the water will evaporate and the concentration will increase. So we only use plastic bottles for solutions that, for example, that contain hydrofluoric acid that would attack glass. The solutions that are not containing hydrofluoric acid and not containing alkali, which also attacks glass, are sold in ampules. Less user-friendly because you can break it open and then the glass shard hits your finger, you've cut your finger, you've got a safety incident, you've got to talk to your boss and your boss's boss and have everybody has to go have safety training and everything else. But it is stable. It is stable, albeit less user-friendly. Lower uncertainty, go back in 10 years, it'll still have the same mass fraction that it did 10 years ago. So ampules, no transpiration, greater stability, longer lifetime, but they can be less pure. Less pure with respect to contaminant elements. For example, if this is a copper solution, you may get a little bit of silicon or sodium leaching out from the glass. Borosilicate glass, you've got Na2O in the glass, you've got B2O3, you've got silicon dioxide that make up the glass. And there'll be slow leaching that will come into the solution. But these solutions are generally themselves diluted down substantial from 1,000 ppm, 1,000 micrograms per gram, down to, say, low parts per million, 1 microgram per gram, 1 milligram per kilogram. That would be a 1,000 to 1 dilution of this solution. 1,000 to 1 dilution of this solution. The bottles themselves, they suffer from transpiration. If you put them in polyethylene terephthalate, trading, but NIST, you're not supposed to say Mylar because that's a trade name, and you're not wanting to advertise one company, in this case DuPont, that owns the registered trademarks. We call it PET. They are resistant to hydrofluoric acid, but they've got the problems with transpiration. Also, acids will make the plastic brittle. If you put like 1 mole per liter nitric acid in a polyethylene bottle, put it on a shelf and go back 20 years from now and then empty it, you may squeeze the bottle and it crumbles in your hands. We've seen that happen. How do we make these solutions? Wherever possible, we take a single element, in this case gold, copper, all of the metallic, almost all the metallic elements with the exception of the alkali and alkaline earths where you've got to use salts because they're very reactive. We dissolve the metal in acid, we get a concentrated solution, we dilute the solution either with a dilute solution of an acid or with water and get about a 50-liter batch of solution which is then bottled. You need to know what percentage of gold is in the gold. What are the impurities in the gold? You have to know that within an inch of its life. Or if it's salt, you need to know the impurities in the salt. You dissolve a measured mass of that high purity characterized material, not losing any. It has to be quantitative. Everything that you put in as the metal has to stay in solution and get in this bottle here. If it doesn't, you've got a problem. Dilute it to a measurement mass, calculate the mass fraction and uncertainty. But you need to back up your value. The way we back up the value is we do an instrumental technique to check the gravimetrically prepared mass fraction using inductively coupled plasma, optical emission spectroscopy, sometimes other techniques, but that's the main technique. It's a primary ratio measurement. It's measured the concentration, the mass fraction of gold in this solution comparing it with the mass fraction of gold in this solution. It's like a balance. A balance is checking one mass against another. If you go home and weigh yourself on a balance, they say there's no standard mass there. It's just you stand on it and measures your mass. Well, the thing is they had to calibrate that scales, you might call it, that balance with a standard mass. And the manufacturer did that. And that standard mass, they've got to check it with some house standard mass that eventually goes back to the standard mass of the weights and measures of the given state, goes back to the NIST platinum iridium number 4 or number 20 through an unbroken chain of measurements, each of which has a stated uncertainty. That's traceability. So we have a couple of strategies here. We have in-house materials that are not sold. We call them NIST primary materials. And wherever possible, we have 2 of these, different lots, different manufacturers. We make one of them, we make a primary solution, also used only in-house. We make calibrant solutions for the ICP-OES measurement and determine the value for the SRM, which is prepared from a second primary material, the gravimetric number. We know the mass of this we took. We know we dissolved it and didn't lose any. That gives you a gravimetric value. If this value agrees with this value, then we have confidence that value is right. And if they don't agree, then you have an uncertainty on each one. What is the uncertainty? If they're discordant, You may have to repeat the work, or you may have to have a larger uncertainty to take into account the disagreement between the values. Strategy B, we don't always have two materials. Then we have the primary measurement, goes to the same chain you saw before, determined value. But here, the gravimetric value is not valid because you don't know what the purity of this material is. So you may be able to dissolve it quantitatively, know you didn't lose any, but you don't know the value you got by this route because you don't know what the purity of this is. The advantages of these strategies, the assignment does not depend on one single gravimetric preparation. If you look here, you see the triple arrows mean we make several different, you don't prepare this solution once, you prepare it 3 or more times here, and you make multiple measurements here. So you want to cover your proverbial rear. The strategy A, where you have two primary materials, it has traceability via more than one material, each of which has a known purity. Strategy B, it makes it easier to prepare SRMs where you do not have a material available in a large enough batch to make the whole SRM batch, but in this case the traceability is restricted to the instrumental measurement. How do we determine the purity of the metals, typically metals, that are used in preparing these spectrometric solutions? In organic chemistry, we use a method called mass balance. You take everything in the material is 100%. From that 100%, you take the sum of all of the mass fractions that were determined, where were detected, and you do a whole survey of the periodic table, and if you detect them, then you may use more accurate techniques to determine the high-level impurities. Whoop. And also, you have other measurements where you do not detect the element, but they have what's called a limit of detection. You have to take that into account because you don't know it's absent, you just know it's below the detection limit. So you take 1/2 of what the limit of detection is and have an uncertainty that covers that, and you have to subtract 1/2 of the limit of detection for the not detected elements. Using the indirect method, step 1, we do a survey technique, glow diffusion mass spectrometry, lasers, scattering mass spectrometry, spark source mass spectrometry, inductively coupled plasma mass spec for a general survey of the whole periodic table. What do they call that? It's a gas analysis for hydrogen, nitrogen, and oxygen, and then combustion analysis for carbon and sulfur. This essentially covers the whole periodic table, and I think this battery may be going dead. It's getting dimmer, I think. Step 2, for the ones that were detected at high levels from this series of measurements, we use appropriate, more accurate methods so that we can get a lower uncertainty on the components here that are detected at high levels here. Now we'll go on to the metacresol purple effort, sulfonephthalein effort. That's Regina Easley. Some of you remember her. She's been about 3 years now at NIST. Jason Waters has been there a little bit longer. He came in 2012. He comes from Frank Malero's group. Of course, she comes from here. Most of the work on obtaining a material of high enough purity comes from Regina. Jason's specialty is making the primary pH measurement with artificial seawater buffers, and then modeling the Pitzer coefficients that you need to characterize activity coefficients at high ionic strength. That's his strong point. Also, a lot of his time is taking up using coulometry as well, doing the coulometric analysis. So you have a primary measurement of pHT or the true PAH of seawater, the activity-based TH of seawater with Pitzer coefficients based on a Hornet cell measurement. Traceability chain, and what I developed back in 2012 to 14, not 1 pH, but 3 pHs where you vary the acid-base ratio. You have 1:1. 1:1 gives you, in tris, about 8.09. Then you have 1 which is higher in acid and lower in base, lower in acid, higher in base. What's wrong?
Can I change out the batteries?
Okay,
You're
yeah.
gonna keep going. Use the keyboard if you have to.
So you have 3 different pHs. Now you can characterize the dye in each of these 3 buffers. And that's Regina's specialty to make the spectrophotometric measurement in it. But you want to spend all the time. This takes months of effort. This takes months of effort. This takes probably months of effort overall. So, so you want to make this effort worthwhile to use a high purity compound for which you could use a lower purity compound, but it's not then it's subject to higher uncertainty because you may have changes in composition over the whole batch, for example. Or there may be lower stability with time if some of the impurities degrade with time. So as a first step in that, what Regina did was do a liquid chromatography mass spectrometry survey of a whole bunch of sulfonephthalein dyes. Bromocresol green, bromocresol purple, you see all the different dyes here. And she characterized, this is assuming that the impurities, she didn't use a calibration of each of the impurities. You assume that the area of the chromatographic peak, or the mass spec peak coming from the chromatographic peak, is the same for each of the impurities. And for and then she took different samples from different manufacturers. She essentially surveyed all the manufacturers she could contact and bought lots and lots and lots of different batches. Sometimes multiple batches from one manufacturer, sometimes one batch from multiple manufacturers, sometimes like 3 lots from this manufacturer, 1 from this, 2 from this. However many she could get. And then she characterized the scatter that she got for impurities, total impurities, as a percent of the total amount of dye present. For bromothymol blue, she only had 1 compound available. 4, 5, 3, 11 for cresol red, metacresol purple. Because of the specific interest of this for pH work, she got 13 batches. And then she measured the percentage of impurity that was apparently present at different wavelengths, because the protonation of the impurities have a different pKa than the intended, the matrix dye. So at the different pHs, different impurities will, if you will, come out of the noise. So the apparent purity is different at different pHs based on the LCMS result. And not only also the spectra of each of the impurities is different, so you measure it at different wavelengths, plus you have different pHs, so you vary the protonation conditions and you vary the wavelength of measurement. And then this is relative area of the total, most of which is the main dye, and you can see the various impurities here of the different dyes. When Regina first showed me this is back when she was still a postdoc. When she first showed me this, she had the bromocresol purple, and that was a yellow graph, and the cresol red, and it was a green graph, and the bromothymol blue was a purple graph, and the metacresol purple was a blue graph. I said, no, Regina, you want the color. Remember, it was like the psychological test where the word yellow was printed in green and the word red was printed in blue and the word blue was printed in orange. So make the color agree. See, now she made all the colors agree, which makes it much easier so you don't have your eyes and your verbal part of your brain clashing with each other. Then after doing the general survey, she went and worked with Benjamin Place, who is a specialist in liquid chromatography, mass spectrometry. That's LC-MS-MS. The HPLC gives you the main component and side impurities. You take a small aliquot of the main component, feed it into mass spectrometer number 1. That gives you the parent peak and maybe some decomposition peaks. You take the parent peak and you put it into a second mass spectrometry, and you get a whole bunch of fragmentation peaks from the parent compound. The parent peak is this minus, what, 1 electron or something like that. And then doing that, and given the masses, you can say, what is the parent compound? And mass spectrometry, it's like taking a bazooka and firing it at a deck of cards, not a deck of cards, but like where you build like a building out of a whole bunch of cinder blocks or something. You fire a bazooka at it and it all falls apart. Now you have to figure out what pieces of the building are left. In this case, the building is a molecule, and then you say these are various compounds which agree with the values of the fragmentation peaks that you see here, like 20906, and I think one of them is, there's 20906, is almost looks like an anthracene type compound. Another one, 30605, is that there? I don't see that one there. 80.96, there's 80.96. I think that was like a phenol type compound or something. Where was 80.96? No, it isn't. I take that back. It's a hydrogen sulfide type species. That's a phenol type, the 93. And you see that. You don't see it there. You don't see it there. Anyway, sometimes these are fragments that she saw evidence for in the LC-MS. That's for small scale. Now, what about, we want to get a kilogram of this stuff because we want to sell this for the next 20 years because we put hundreds of thousands of dollars of labor into characterizing the measurement. We want to be able to leverage that over as long a time as we can. So these are, company 1 had a large batch, but you can see these impurities. These are 5 batches from here, from Bob Burns' group, and you can see they're much purer. They have much lower. This one is a little bit worse than these guys. These have 1 impurity here, but generally they're much better than the product of this manufacturer. 99.7 to 0.9, 98.75. So you can see these other peaks are lowering the purity over what the USF batches show. The company used the essentially an what do you call it, not up-ramped, a scaled-up version of the USF isolation purification procedure with the cedronitrile, and they got a very good purity, but it was too expensive. We wanted to pay $70,000 for a kilogram. They couldn't meet it. 250 kilograms, they still couldn't. 250 grams, a quarter of a kilogram, they still couldn't do it. So they said, we want to use another procedure that's less expensive, but when they did that, there were a lot more impurities, and it came down to 99.7%. And one of the commercial companies sells, you could buy from that company a large batch, a 1 kilogram batch without additional purification. We may have to go that route, but that's not the desirable route.